We're very happy to have Jens Eisert here from the FU Berlin, who will talk about the tensor network approach to an AdS qCFT correspondence.
Oh, wonderful. Thanks so very much. Thanks for the kind invitation. I hope you're all well in these somewhat eerie and awkward times. And thanks, of course, to the organizers for setting up this very nice, now virtual workshop on tensor networks from simulations to holography. And well, maybe unsurprisingly, this is what this talk will be precisely about when we have a look at what could be called a tensor network approach to an AdS qCFT correspondence, where the Q is actually no typo, and the chairman has nicely pronounced this, but refers to a CFT up to some quasi-regular symmetry, picking up a theme of Frank's talk earlier on capturing critical states in terms of tensor networks, although in a slightly different flavor. So this theme has been quite a long and winding journey for us, and I've decided to tell the story from the beginning on. So the good news is that we will be very much faithful to the theme of the workshop. The bad news is that I will have some overlap with what I've spoken up at the last year's meeting of the same series. So sorry to those who have attended the workshop at the time, but for a nice consistency of the story and to set this into the context of our own journey of the subject. So we begin the journey by recapping what so-called Matchgate tensor networks are and what way they provide nice hands-on and concrete handable toy models for capturing aspects of holography. Then we will move on to discuss a picture of Majorana dimers, a spaghetti picture of Majorana sitting on some tiled lattice that is in some ways even more concrete and gives also a connection to holographic quantum error correcting codes, and see how this already sets the stage to capture critical theories sitting on a boundary setting. And in the third part, to finally come to Majorana dimers, quasi-periodic chains, and qCFTs, where we can see that we can explicitly construct tensor network models that actually match conformal transformations if you want, but only quite so, like up to a quasi-regular symmetry of the lattice. One can map out conformal symmetries of a problem. We can do kind of lattice conformal field theory in a tensor network language. And if time allows, I'm not quite sure what the habits are concerning the time slots and so on. I will, since this is a tensor networks workshop and this is a bit of a connoisseur's topic, I will briefly mention a couple of other tensor network activities that kept us busy on using PEPs in an out of equilibrium many-body dynamics, new construction rules for PEPs, and also a bit on using a tensor network machinery in probabilistic modeling and notions of machine learning, something we are quite interested in and busy with these days. But again, that depends on time, interest, and how we go with everything. But let's start at the very beginning with our journey, and let's have a look where this all comes from. So there's probably quite little I need to say at this workshop of this correspondence. The AdS CFT correspondence as a correspondence between two quite different physical theories after all. That's on the one hand, Einstein gravity in d+1 anti-de Sitter spacetime, or the other a conformal field theory in d+1 dimension that is sitting on the boundary of such a construction. So the geometry is that of a hyperbolic plane, two spatial dimensions. So in the Poincare plane, if you want, this would look like in this picture here, where all the triangles in the picture could be seen as having the same size. So this duality as a dictionary between these two different physical theories has obviously created a huge attention since it was postulated in '97, and since, well, we all know that citations are a very bad figure of merit after all, but it does say something that, to my knowledge, the like 2 of the 3 papers mentioned below are apparently the 2 most cited papers in physics, at least to my knowledge. What's also clear, and that's also part of the founding principle of this workshop series, is that recent years have seen quite some interest in becoming more concrete and develop some sort of hands-on tensor network models that map out some of this correspondence in a very concrete and manifest and efficiently describable fashion, connecting to notions of condensed matter theory on the one hand, and notions of quantum information, specifically that of quantum error correction on the other, hoping that one can grasp more specific features of this. And this is also basically what the point of the main part of the talk is before we come to the Outlook session on something quite different. So the starting point is based on ideas of quantum error correcting codes, and it's called what is called the Pentagon code, and can be seen as a toy model of some of the ideas of quantum error correction that have been put forward in the AdS CFT context, prominently by Harlow, but also of others. So what this starting point of our journey does is that it takes a uniform tiling of some hyperbolic space, a tessellation, and on each of these vertices one places some tensor. So in this way, as it's set up, the tensor network has no inherent directionality, and all the locations in the bulk can be treated in the same footing. And say if an animal placed there, it would kind of see every place in the tiling in the lattice in the same fashion. Now in this Pentagon code construction, the tensors placed there and the states are obtained upon construction of this tensor network have a very strong property, a very awkward property, in a way an excessively strong property, that what is called perfect tensors. So this means concretely that if one selects any collection of edges of this tensor, including the guy coming out into the bulk, forming one subsystem A that has fewer edges than the component, then the tensor that is obtained in that fashion or distributed in that fashion would be proportional to an isometry from the legs on the A side to the complement. And not only that, but this is a property that should hold for every such cut. So this is a bit of a funny and a somewhat awkward property, and it's not so clear whether such a perfect tensor would exist in the first place. But well, they do, at least for several tensor degrees. It has been looked at in many settings. There's also some no-go theorems in some dimensions. In fact, if one treats the tensors as representing the coefficients of a pure state in some basis, so by flipping the legs down and seeing this as a tensor network representation of a pure state, then the perfect tensors are exactly what is called in quantum information and quantum error correction, the so-called absolutely maximally entangled states, which means that it would be a pure state that according to every cut of that kind, again to the same bipartite split, be a maximally entangled state between any cut of this type. Now, if one puts those tensors with degree 2n+1 on some hyperbolic tiling, then one has like the legs sticking out. That would be the bulk degree of freedom. And the 2n-1 neighbors to the neighboring ties of this plane. So since this tensor is a perfect tensor, so an isometric tensor, it gives rise to an isometric mapping from the guy coming into the neighbors. In fact, an isometric mapping of a quantum error correcting code. So if the logical spins are spin up and spin down, being fed into the bulk degrees of freedom, this will be encoded in a quantum code word involving 2n-1 spins. And in the quantum error correcting language, this would be a 2n-1 1n code, where the first number is the physical number of qubits in the code. That would be 2n-1. The next number would be how many qubits is encoded, like the bulk degree of freedom coming in, that would be 1. And the third would be the distance of the code, which is the minimum weight of a Pauli operator to go from one logical code word to another. In some way, the error correcting capability or the strength of the quantum error correcting code. So the specific tiling chosen, like in this picture here, you would have 5 neighbors, hence a pentagon code. And this will be our example later on. Also, when we go on to describe this qCFT construction, the tensor network is a handy example of that type. So that's just a tensor, not a tensor network. But this state, the tensor network, is obtained by placing identical tensors on all the sides, and the state on the boundary is obtained upon contraction. That would be the holographic state if one puts a product state vector into the bulk degrees of freedom and then gets the respective holographic state out at the end of the day on the boundary. So based on such a construction, one can indeed reproduce a number of properties that are queued, and that is, that was not, this was what I just showed before. One can construct a number of properties that one expects from the continuum theory in a kind of lattice version, as a very hands-on lattice version of some kind. For example, there is the famous the entanglement entropy of a connected region of some boundary would be the entanglement entropy on the boundary. That's in fact connected to the length of the minimum bulk geodesic. This is a statement like of the Ryu-Takanayagi formula in the continuum, and this is seen as an upper bound directly from the tensor network picture, and then also from the error correcting capabilities, one would find that this is exactly matched as the length of the minimum bulk geodesic. So this is again a kind of a lattice version of the Ryu-Takanayagi formula after all. So this is a nice kind of lattice manifestation of the connection between quantum error correction and holography that has been put forth prominently by Harlow and by others, where it has been suggested that the bulk degrees of freedom would be protected against erasure of parts of the bulk degrees of freedom. And indeed, this is seen here as a very manifest version, as not an approximate, but as a precise quantum error correcting code on a lattice, although a bit with funny properties from a quantum error correcting perspective, in that the error correction capabilities depend on how far away you are from the boundary in this setting. But still, the whole code would be a stabilizer code, like a qubit stabilizer code with known properties and known distance. So that's kind of the first picture here of a pentagon code that makes the connection between holography on the one hand and notions of quantum error correction on the other manifest in a precise fashion, where one can also derive properties like the Ryu-Takanayagi formula from quantum error correcting capabilities of this holographic state. This is the first picture. But to be fair, the boundary state is far from a reasonable CFT, although we will come back to this claim later in the talk. But it has a bit of an awkward property. It would have, as a stabilizer state, 0 correlation length. So the correlations are a bit funny. Let's look at this later in the talk. The second picture is one of tensor networks consisting of isometries and disentanglers, the famous mirror picture, where we have a kind of this layer structure of these tensors of a different type. And it has long been suggested, in fact, that's where the mirror picture comes from in the first place, that such a mirror would be a wonderful place to capture critical phases of matter. And indeed, this is known that this mirror tensor network approximates critical quantum states well that are here realized on the boundary. That's just the tensor network as such. So one has to fill the tensors with meaning. It has been quite nice work of Evenbly and White, and also following up other work by Evenbly and Vidal on using a picture of that kind for free fermionic systems, and then relating the states that you get out at the end of the day to a wavelet transform to go from one step in the hierarchy to the other. And this is also a picture we want to relate to. And the last one is that of random isometric tensors, where you do, like, again, have a tiling of a plane, and then you place a tensor there, but the tensor is not taken to be fixed, but in fact random, random, and then using the usual machinery of random tensors, one finds that with high probability, the tensors are close to being perfect, and then using the arguments of before, one finds that with high probability, to a good approximation, like the Ryuta-Ganayagi formula would be realized on the boundary, not for these fermionic settings, but for these random tensor networks, which is a nice feature, which we are also in the process of relating to the Matchgates, and I might say something about that later, or we might discuss questions of this type. So these are 3 pictures of a connection between holographic descriptions and tensor networks, and our starting point of our journey was to find a way in which one can relate these pictures and embody them in a larger framework that would see them as special cases, but that we can tune things better and relate them to a kind of more physical context, and also see the CFT nature on the boundary better in a tensor network picture. Which brings me to the first reading of things in our 3 readings of Matchgates, of Majorana dimers, and what we called qCFTs on Matchgate tensor networks. So what is a Matchgate tensor network? So the starting point is the same as before. We choose some tiling of the plane, and on each of these tiles we place a tensor that has still a quite strong property, although not quite as strong as being perfect, but would be what is called a Matchgate tensor. That's the tensor on each of the sides. And again, the boundary state would be obtained by the tensor contraction of all the closed all the connected indices in the bulk of the setting. If you want, you can place also a bulk degree of freedom there, but this is not so important for what follows. This is a bit of a matter of taste, whether you would have them sticking out or not. So what is a Matchgate tensor? Here's a property that may look a bit awkward, involving a Pfaffian of a matrix and a submatrix here. The upshot is that this condition of being a Matchgate tensor is the one, so that if you have a tiling of the plane and pick a local ordering of your spin degrees of freedom, you can see this as a kind of local Jordan-Wigner representation, so that upon contraction of the entire tensor network, you would get a free fermionic non-interacting Majorana state on the boundary. This would work for any planar graph, but it's kind of the consistent spin representation to, upon contraction of the tensor network, get a non-interacting fermionic state out at the end of the day. So for a given reference index, the characteristic function that you get would be just governed by an antisymmetric matrix, which is basically all there is to say. So each of these local tensors would be governed by an antisymmetric matrix that is sitting on the tensor. So that's all there is. For each of the Majorana, you would get one entry of this antisymmetric matrix. So the idea of a Matchgate is very old, but and it has a long and winding story. Bravi also made interesting contributions on arbitrary Matchgates on planar tensor networks. What our contribution was here is to make to formulate consistent and hands-on rules so that you get self-contraction under control and simple contraction rules, so that for an arbitrary planar graph of that type, you would end up with a consistent algorithm that would not only be efficient, but also practical, that would allow us to construct an arbitrary tensor network of that kind. With here in this tessellation of the kind mentioned, would be doing that with an L squared n number of steps for L boundary sites and L contracted tensors, but it's a versatile setting that could be used for all kinds of that form, that if you place the antisymmetric tensors there, you would, with small numerical effort, be able to construct that for very large system sizes. So the upshot is you place some generating matrix on some tiling, and that is what you need, and then you can get the boundary state and start playing as a very nice, concrete, hands-on and manifest setting. Good. How powerful is that? Well, the first insight is that it already relates to the pentagon code mentioned, in that the holographic pentagon code with computational basis states put into the bulk degrees of freedom does give rise to a Matchgate tensor network at the end of the day, if one interprets the stabilizer code as a Majorana setting. So the code words seen as fermionic states would be precisely matched by a Matchgate tensor network of that kind. That's not a new insight, not a new result, but it's a new picture of the same thing. And it's nice to see that the Matchgate tensor network picture is already powerful enough to embody the known picture of pentagon codes formalized as stabilizer codes here in a Matchgate picture. So the Matchgates are at least as powerful as the stabilizer codes of the pentagon code, relating the quantum information language to this picture of Matchgate tensor networks. More interesting is the connection between geometry and properties of this state. And the nicest and cleanest way of seeing that would be one where you have the simplest flat tiling of the plane. So that would be a 3-6 tiling in terms of the Schläfli symbol, where this means that the first number is just the number of vertices per edge, and the second number would be the number of neighbors around each edge. So the 3-6 tiling is nothing but the flat tiling of the plane. And you could say just place an antisymmetric matrix A there with some parameter, and then see what you get if you just have the same A all of the sides, what you get as the boundary state at the end of the day if you contract all these tensor networks. And what you find is a gap theory. In fact, one finds a nice exponential decay of correlations over like orders of magnitude if you do it right. So the correlations would be exponentially decaying, and not only that, the decay of this of these correlations can be tuned with this one parameter that you have in the lattice side, in the antisymmetric matrix. So it's a kind of a family of gap theories on the boundary, but one where we have a knob, and you can tune the knob and tune the decay of the exponential decay of correlations on the boundary in a kind of one parameter family of states, except for one point, but I will mention that later. So if a flat tiling corresponds to a gapped theory on the boundary. What happens if we kind of bend the system a bit and look at a negatively curved setting, like a hyperbolic setting, which would mean that in this Schläfli symbol notation, we would have like a 3K tiling, where K is the number of neighbors larger than 6, so that you bend the thing down, and it would be a discrete approximation of a hyperbolic tiling of the bulk. And again, one can take a Matchgate and take the simplest antisymmetric matrix that's isotropic on each of these sides with, again, a single parameter, and see what happens if you have a negatively curved bulk, and see what happens to the boundary that you obtain in such a fashion. What does happen is that you get a critical theory, again, with the right correlation decay over large distances. So you find an algebraic decay of correlations in the boundary state, but again, one that's acutely tunable by this parameter. So you can basically give me a power law, and I can find a parameter A, so that the decay of correlations, the polynomial decay, would be precisely matched by the given decay. So you can really tune the power law by tuning this one parameter. And you can also pick the right values to get the critical easing theory or copies thereof that would be matching the conformal field theory. you get a critical state for a negatively curved setting. So you get a connection between the curvature on the one hand and the boundary state, in that you go from a gap to a critical theory on the boundary. So that's kind of already a nice playground to look at this setting. This is just about correlations and a bit basic and plain. So how about the entanglement entropy of a region of the boundary, to kind of give more meat to the idea of having a proper critical system at work? Here we know this famous CFT entanglement entropy formula of a block, going back to work by Halsey, Larsen, and Wilczek, and also to Calabrese and Cardi, that found this formula for the entanglement entropy for a conformal field theory, which can here be again mapped out, and one sees a very nice correspondence of the Matchgate tensor network model, not only on the level of correlations decay, but also on the level of CFTs, that they have the right scaling and match out the CFT predictions for the appropriate values of the conformal charge. How about MERA? I promised to relate what we had to different pictures, to the different pictures we stated at the beginning. So how can you relate this Matchgate tensor network to the MERA picture? Well, you can it in the way that you can take, say, the topology of the MERA network with 3, like 1 coming in, 2 coming out, and 4-leg MERA tensor networks, 2 coming in, 2 coming out, and see what happens to the boundary state that you get at the end of the day if you place the respective tensors on these sites, with now three parameters that you can tune. And interestingly, if one does that, one finds a relative energy density error to the continuum solution of about 0.0002 with the smallest bond dimension you can pick, and the appropriate choice of the MERA tensor, of the Matchgate tensor networks, to match out the critical theory on the boundary with appropriate refinement for higher bond dimensions. So this is here the correlation matrix as a function of the distance for the bulk tiling on the one hand, and on the MERA with 256 sites. And again, it's remarkably translation invariant, although MERAs are not strictly speaking translation invariant. It's an approximately translation invariant manifestation of a MERA, although this is more like a Euclidean setting, because the match gates can but don't have to be unitary. You get an efficient construction either way. So that's different from the asymmetric MERA, but that is a setting where you can realize a translation invariant state on the boundary in a MERA ansatz to actually remarkable accuracy after all. This is just for the correlations and entanglement decay. We worked hard in this first paper to also get other conformal data for the tilings and for the MERA out, and then we've seen that the scaling dimension and the fields and the structure constant are mapping out the continuum theory quite well for a very small bond dimension compared to the other tilings and also the wavelet MERA. So that's a kind of nice setting that with a very small number of parameters, one can get the critical theory out. One arrives at an almost translation invariant state, although the MERA ansatz again is not quite translation invariant, but the state you obtain would, to a very good accuracy and precision, be a translation invariant state. And you can also extract a wide range of critical data at the end of the day if you tune things right. Okay, this is a nice playground. Let's go to the second reading of our setting. We're 28 minutes into the talk. I promise to be not overrun in time. I'll keep it rather short. But let's get a bit more serious on the quantum error correction part of things. So in order to go away from efficient constructions and become more analytical and insightful, and all what follows will be largely analytical, let's not make things simple, more complicated, but simpler by looking at the intersection of match gates and stabilizers. And if this sounds cryptic, in fact, if you stare at the pentagon code, you've seen this is a match gate, or it's reflected by the match gate framework, but at the same time, the ground states of the pentagon code would, as ground states of a stabilizer code, be like stabilizer ground states. So we can look at the intersection of stabilizer world and Matchgate world and find that this intersection is way more interesting than one might think. We were quite surprised about that you can see this as a picture of paired Majorana dimers that sit on the boundary of some tiling. So the whole state would be governed by labeling what Majorana on the boundary would be matched with what other. So this is a directed graph because the order matters. And this matching would be just the state that you would get for like a pentagon code word that you have for each code. The cute thing is that this doesn't apply only to a code word of some tensor, but this can be uplifted to a full tensor network, and one can arrive at not only the logical state spanned by some basis factors, but one can find the full tensor network of a paired Majorana dimer as a kind of a spaghetti picture of Majoranas on the boundary that you get in terms of simple contraction rules that would map to simple rules how to glue the spaghettis together to get a state on the boundary that is just a connection of paired Majoranas sitting there. So the upshot is that stabilizer quantum error correcting codes that are seen as Matchgate tensor networks can, in an analytical fashion, be grasped by the appropriate matching of Majorana fermions that sit on the boundary of the setting, and everything is said to be said about the setting if you find the matching of those Majoranas, which is now simple enough that you cannot only do this numerically, which you can also do, but in fact in largely analytical terms. So this fusing of dimers, so the connections, the contraction of tensor networks would be some sort of fusion setting of dimers along edges. So there's consistent rules of how to glue these spaghettis together so that you would get the pattern of Majoranas sitting on the boundary at the end of the day if you put that together and formulate the full intersection of Matchgate models on the one hand and stabilizer codes in a quantum information language on the other hand. And this is a very nice picture of holographic codes where one can now no longer numerically but also analytically say a lot of things that one could not say otherwise, and it gives rise to quite powerful machinery to end up with rigorous analytical statements of some sort. For example, one finds that the computational basis state vectors of the bulk are dual to Majorana dimer states on the boundary, and one can compute second moments of non-Gaussian states also arising in quantum error correcting codes, which means that if you don't put like binary words into the bulk, but in fact coherent quantum information, one can still compute moments and properties of the now full quantum error correcting states out on the boundary, not as a classical state coming in, but as a kind of quantum setting of a quantum state being fed into the bulk, and one can still compute properties of the boundary state that comes out at the end of the day. One can also compute Renyi entropies, so two Renyi entropies, at least like integer Renyi entropies, again in a consistent fashion by keeping track of the paired Majoranas on the boundary. And that's a kind of consistent spaghetti picture of computing polynomial expressions which are of an integer type, so that you can kind of compute Renyi entropies on the boundary of reduced states on the boundary, and can compute the scaling of entanglement entropies, not again numerically, but in fact in mostly analytical terms. So the upshot here is that the Matchgate tensor networks provide a versatile framework allowing for new insights into holographic codes. The Matchgates alone already provide a fun playground because you can look at fermionic mirror, you can look at the connection between geometry, curvature, and properties of the state. One can relate this to critical theories and kind of map out the kind of the various setting of the connection between curvature and state properties. One can find the connection to quantum error correcting codes. In this picture of Majorana dimers, one can also, in analytical terms, connect error correcting capabilities to boundary properties and also compute properties of the boundary state that one could not do otherwise. Now in analytical, but not in numerical terms. 34 minutes, which brings me to the last part of the talk as a third reading of our theme on quasi-periodic chains and what we call qCFT, so quasi-regular CFTs. And to be concrete, let's look here again at the pentagon code as our workhorse, although it should be clear that this works also for all of the mentioned holographic codes, not only the pentagon code, but the idea is quite instructive after all. So let's look specifically at the 4-5 dual of the 5-4 pentagon code, again captured in terms of Majorana dimers. So the first insight is that one gets a quite cute picture of holographic quantum error correction, where one can see that on the left-hand side, you see the dimers sitting on the tiles themselves, on the original code words of the specific tiles. On the right-hand side, you see the full constructed tensor networks with a spaghetti picture, and you see that there's a geodesic structure emerging so that the paired Majoranas just follow the geodesics of the setting, and properties of the quantum error correcting code can be seen as arising from this geodesic structure on the right-hand side. But maybe more to the point of the state obtained, I claimed earlier that the state on the boundary is somehow funny and that there's like funny correlation properties. That's kind of true, but a more careful reading of this finds that if one looks at the say entanglement entropy obtained on average, if you average over translates on the boundary, you find that this is not so far away from a conformal field theory with some conformal charge, which is like non-integer. But in fact, one finds that the entanglement entropy formula of a CFT is actually quite nicely mapped out, but only on average on the boundary. So if you look at this, this looks like a CFT, but with some funny non-integer conformal charge. So in fact, one can kind of like look at this in more detail and look what this does as a function of the length in terms of the entanglement entropy, where one finds the logarithmic growth of the entanglement entropy as expected from a critical theory. One can look at the correlation decay, and not only is this found to be like of a 1 over distance type on average, again, averaged over translates, but this can be also analytically found that you really get the 1 over d decay of correlations in the pentagon code, something that's very hard to come by in the stabilizer code setting. I wouldn't know how to do this, but here you get in the Majorana picture, you get the 1 over d like power law decation correlation decay on the boundary in an analytical fashion, again reminiscent of a CFT-like correlation follow. There's also in fact, one can see a number of cute things that one expects in the continuum picture. And what we see is very much the structure of a conformal field theory, but now in a fractional fashion, where the fractional central charges suggest some sort of aperiodic, quasi-periodic setting sitting behind, an aperiodic, strongly disordered system sitting behind there. So a number of cute things that one expects in the continuum picture can be realized here, but now in a kind of approximate lattice fashion. For example, this famous Brown-Hainaut formula that relates the relative growth of the boundary if you go from like outside to the boundary with the geodesic length through the bulk as a relationship between this length and the boundary, where this coefficient that relates the two would be like 2 alpha in terms of the AdS radius that roughly matches out the curvature of the problem, where this is related to the conformal charge of the problem. In the lattice version, it may be true that the specific geodesics will very much depend on the tiling of the plane. But if you see the discrete setting in a way where you go from one refinement to the next in some iterative fashion, you would asymptotically get precisely the same Brown-Henault formula as a discrete version going from one lattice to the other. So there's a kind of a discrete Brown-Henault formula at work. And the underlying picture here is just that one of a quasi-regular structure. So what is that? You think of the entire tiling as a tiling, like as an onion, where we have different layers from the middle layer to the next layer and so on, where on each of these layers you would have these patterns of Majorana pairs that give the content of the lattice. So the lattice itself would have a quasi-periodic structure, which means that you can label each of these vertices with A or B. And then there is an inflation rule that will tell you start from a vertex A and go to the next. You would map a vertex A to ABA, a B to ABABA and something. And then that's the rule of going from one layer to the next. And then you would apply this rule again to this layer, go to the next layer, and so on. And this would be the rule of getting the words on later realizations of this inflation rule. And it would be quasi-periodic in the sense that for a sufficiently large number of invocations of this inflation rule, you would get an equal distribution of all the letters on the boundary. So that's the symmetry of the lattice as such, and not the state itself. But now the Majorana picture is so simple that you would place these Majorana pictures on top of that realize a quantum state with a respective quasi-regular structure. And this picture is simple enough that one can formulate inflation rules not on the level of the lattice as such, that's just the geometry of the problem, but you can find inflation rules on the level of dimers, what happens when they don't cross and when they cross. So the consistent rule of going from one layer to the other to get a state out at the end of the day. And then using ideas of strong disorder renormalization that like also our co-worker Zoltan Zimburos has looked at in the context of paired fermion pairs, not Majoranas. One can go as far as using these rules and iterating them to come up with exact formulas for entanglement entropies and other properties of the boundary. So one gets like formulas, but no numerical ones, but one gets from infinite sums asymptotic entanglement entropy expressions from states that have this quasi-periodic structure. And that's precisely the CFT formula. So on average, you get a CFT-like behavior of the state that's almost like a CFT, but up to this quasi-regular symmetry that's dictated by the lattice. And that's something that one can really push to the end. So one can develop a picture of a quantum state sitting there, and it has all the structure you want, all the settings you want, except from a CFT that you would have the quasi-periodic structure of the problem that you just inherit by the very symmetry of the problem that's captured by the inflation rules from going from the inside to the outside. So a quasi-regular CFT would be a discretized quantum field theory that is invariant under discrete global and local scaling transformations that exhibit approximate translation invariance. It's not quite translation invariant, although to a very good approximation. And you get a critical state, a CFT with all the entanglement entropy formulas, not numerically, but exactly and analytically, sitting on the boundary, except from the quasi-regular structure. I can also see of conformal transformations, which up to quasi-regular symmetry would be just the ones of the CFT. One can think of global scale transformations, translations, local scale transformations, special conformal transformations realized in this setting, except for a quasi-regular symmetry, which would be just a restriction of the full set it's a subgroup of conformal transformations where you would do the same conformal transformations, but up to the constraint that the lattice is a quasi-regular one. So you get a quasi-regular CFT out at the end of the day. The pentagon code is a good example thereof, but all the other holographic codes that are describable by paired Majoranas would be describable in the same fashion. So one gets a tensor network picture of CFTs to a very good approximation, only to the approximation that are not quite translation invariant, but almost, that is dictated by the quasi-regular structure of the problem. So that's basically a very concrete, basically almost like a formula of the CFT in tensor networks sitting on the boundary, again, up to this conformal, this quasi-regular symmetry. Which brings me to the end of the main part of this talk. So the lesson is that the Majorana dimers that come from this picture that we have developed from Matchgates and quantum error correcting codes give rise to quasi-periodic chains, the entropy of which corresponds to tunable non-integer central charges. And seen from a wider context, this is basically a parameterization of a conformal field theory, if you want, but almost, except that you have a quasi-periodic structure from the tiling of the lattice. But other than that, you would basically get a concrete and hands-on and formula-like picture of a CFT sitting on the boundary as a tensor network picture at the end of the day. Which brings me to the end of my talk. Well, I keep it short. Maybe I have 3 slides that I just throw at you. If you're interested, I might say a few words about this. This has been a bit of a connoisseur topic. We've been quite busy with this over the time, developing this further. There's lots of other tensor network activities in the group. So over the year, we had specifically many activities relating to tensor networks to capture real condensed matter systems in quantum materials. Also collaborated with experimentalists nearby, where we, for example, looked at a new kind of spin liquid with a funny frustration mechanisms where you have 2 Kagome lattices in a double layer structure in an actual quantum material that they have in the lab, where the properties that they have measured in the lab are being matched by a kind of an IPEPS numerical algorithm that has been designed to capture that type of quantum material, questions of equilibrium dynamics for many body localized systems in quantum time crystals, where we looked at Fouquet type, disorder type of readings to capture with IPEPs and the appropriate local physical systems, appropriate non-equilibrium problems of some type. Here we also collaborate with our friends in Garching on doing experiments of that type called atoms. So this is a lot of development of machinery for tensor networks to kind of capture quantum materials in the lab, and also called atoms in the lab of kind of matching out what you can do with real strongly correlated systems from the tensor network perspective. With our friends in Ghent, we've been thinking about new construction rules of PEPs and looked at specifically efficient variation construction of 2-dimensional tensor networks in a WUMPS type for a non-trivial unit cell that's not eaten up if the unit cell is large, but is still efficiently scaling in the unit cell. And maybe the most unorthodox picture that we've been thinking about, and that's my last slide, but that seems like an extremely forward-looking field, is to use the machinery of tensor networks not to describe quantum states, but to see this as a toolbox to do probabilistic modeling. So where you basically think of the legs coming out as describing probability distributions and see what the potential is of using tensor networks in notions of machine learning, probabilistic graphical models, and other notions of probabilistic modeling, where there's actually quite some surprises in the power of tensor networks. If you look at separations between different classes of that, I'm happy to say more, or of using tensor networks to describe quantum states, nor of distributions, but in fact, to describe function dictionaries, to capture functions when you want to learn dynamical laws, nonlinear dynamical laws from data. This is kind of nice that you can observe nature and learn what the underlying unknown physical law is at the end of the day, but in a scalable fashion using tensor networks as a fresh mindset here. It's a fresh machinery because that's not commonly the playground of tensor networks. They provide very nice scalable tools to learn unknown dynamical laws like in turbulence, in nonlinear equations of motion, like nonlinear coupled systems from data alone in a kind of data-driven mindset. I'm happy to say more. We had a NeurIPS contribution here that's going to come out on this kind of using tensor networks in this context. Which brings me to the end of this talk. We had a long and winding journey that started out with our endeavors of using Matchgates to capture holographic properties of systems, where we found this nice playground to relate geometry and properties of the state in various fashions, and also relate to a mirror picture, to a pentagon code picture, and so on. Moving on to understand this in a picture of paired Majorana dimers, to then, in the end, map out the setting of quantum error correction and Majorana dimers, and to develop a picture of a CFT in terms of Majorana dimers. That's almost like a CFT, but not quite, except that you have this kind of quasi-regular structure. But if you give up full translational invariance, but have a bit of the quasi-regular structure left that comes from the symmetry of the problem, then you can go all the way to get formulas and kind of map out things exactly in a tensor network picture. It's not quite a CFT, but what we call a qCFT in a very concrete and hands-on fashion. For reasons of time, I keep just in time. It's 50 minutes. So I thank you very much for your attention. I'm looking forward to questions you might potentially have. Thanks for your attention.
Yeah, thank you very much for this very nice talk. If anyone has questions, please just unmute yourself and ask it, or you can also raise your hand, whatever you prefer. So questions. So I could make the start. So with the qCFTs, have you looked at excitations? Because they would locally break the regular symmetries of the tensor network, right? Have you looked into this?
We have done this. Well, it's very hard to do this analytically, but numerically, this can be easily done, and we are just looking at this also together with Suki on what happens in the dynamical setting, and then you can kind of relate dynamical properties of the bulk to dynamical properties of the boundary. And I might even show some pictures. I'll wait for another question. I can kind of maybe see whether I find a picture. This can be done. I mean, the setting is concrete enough that you can do this either in the Matchgate or in the paired Majorana picture. You will get expressions that make these questions answerable, but of course no longer in analytical terms. But since you have this kind of efficiently contractible setting, you would be able to do this for large system sizes in a concrete fashion. Mm-hmm. Indeed, you're absolutely right.
Okay, thanks. So we have a raised hand by Shunyun Kao. You could just unmute yourself and ask the question.
All right, thanks, Jens, for the great talk. I'm just a little confused about the connection with the perfect code, because as far as I know, the latter does not have power law decaying correlation on the boundary, whereas your Majorana dimer model seems to have an approximate power law decay. So what has changed?
You mean that the pentagon code would not have this, or what do you say?
Yeah, I was under the impression that because the pentagon code is in stabilizer code, right? So in the computational logical basis states, you wouldn't have power law decay and correlation function on the boundary.
Well, you will get, this depends on, you will get this power law. This is not easily obvious in the stabilizer picture because as you say, it's a ground state of a stabilizer problem. But if you go to the boundary and identify the boundary spins with Majoranas, you will indeed get 1/d correlation decay, but just on average. It's just kind of the pattern of correlations. You would get like funny jumps, but on average, you will indeed get the power law of correlations, also in the pentagon code. This is not obvious. I mean, in fact, it's not obvious from the original stabilizer code spin picture, but you will get on the boundary in like in the pre-image of Jordan-Wigner, you get a 1/d correlation decay if you average over translates of the boundary. So that's, in a way, that's also kind of a cute insight that you get this kind of correlation decay that's not manifest because you get this apparent zero correlation length, but through the connection of spaghettis coming in, you would get on average this 1/d correlation. So in a way, the original pentagon code is not so far away from a CFT, if you want, viewed from that perspective. Is that a fair answer to your question, or have I confused you more than I have gained? The short answer is you do get this 1/distance correlation decay, also in the pentagon code. You just don't see it so obviously.
Right, so it has something to do with averaging, but it's not entirely clear. So, but yeah, it's
indeed, it does, and the averaging is just the averaging over translates. Or you take a correlation, then you just average over the shifts, and that's what you get.
Yeah, okay, I see. Thank you.
Okay.
Okay, are there more questions?
Yeah, I'd like to ask a question. So yeah, thanks for the talk. I would like to ask where the geometry comes into play. So are specific tilings that you presented known to represent, for example, an AdS geometry or hyperbolic geometry, or how do you relate specific tensors to a hyperbolic geometry, for example?
Well, I mean, the lattices are just the tilings of, I mean, the geometry, this quasi-regular structure is just the property of the lattice. And that's basically like a lattice version of an AdS spacetime, if you want, in the same way as the regular tiling of the pentagon code would be a discrete version of the AdS spacetime. So this quasi-regular structure is just the structure of the tiling itself, whereas these states on top of that are a very simple manifestation of states that inherit that symmetry. But the tilings as such, that's very much relatable to I mean, that's just basically a tiling version of an AdS, like a time slice in AdS spacetime that you would get. That would be precisely the geometry of the lattice. And again, the states would be the ones that would that inherit that symmetry. In generality, that's very hard to capture and difficult to come by, but that's kind of the nice thing about this paired Majorana picture, that you would get a state that's simple enough that you can construct properties and derive things and also compute things analytically that specifically manifestly have the same symmetry of the problem. But I mean, the tiling that I mentioned, like the pentagon code, is a very nice example that in a way that you know very well would be like a discrete version of an AdS spacetime if you want, but it would have this quasi-periodic structure of the type that I have just mentioned.
Okay, so I'm seeing no more raised hands, so I would say we could stop here. Thank you very much again for the talk.
Thank you.